Hello, my name is Avery Finch, and I am a senior at the University of Dallas. I'm currently completing my semester of student teaching at Britton Elementary in Irving Independent School District. In this video, I'll be teaching a 4th grade science class, which consists of 15 students, 7 of which are girls and 8 of which are boys. 6 of these students have been categorized as English as second language learners, and 2 have been diagnosed with attention deficit disorder. In this lesson, students will be exploring motion in the forms of kinetic and potential energy. This class should have explored the basics of the forms of energy in 3rd grade, so this will be providing a review of some material, and some material will be newly introduced and building on what they have in their prior knowledge. A whole unit of energy is being covered over the entire week, but for this particular lesson, I am teaching the students about potential and kinetic energy. To observe potential and kinetic energy, the students will be creating pendulums and determining at what point the pendulum has potential or kinetic energy. There are 2 ultimate goals for this lesson, the first being that students be able to differentiate between the forms of energy. Because the unit is spread out over a week, students will have ample time to focus on individual forms of energy and able to conduct experiments to physically witness the forms of energy in motion. In this particular lesson, by creating and observing the pendulum in motion, students will be able to correctly identify when an object has potential or kinetic energy. The second lesson is that students will be able to collect and record data by observing and using descriptive words, labeled drawings, and writing. Before, during, and after the lesson, students will be making predictions and recording their observations in their journals. At the end of the lesson, the students will be drawing a pendulum and label the different parts and label where the pendulum has potential or where it has potential kinetic energy. Doing this will also contribute to the success of goal number 1, helping them determine the forms of energy. I hope you enjoy the lesson. Thank you.
Statement. Oh, well, nobody said.
I'll let them know. Alright, let's do today. So today we're going to be talking about thermal heat energy. What did we talk about 2 days ago? We talked about potential and kinetic. Who can tell me the definition or their own rendition of a definition for potential energy? Eduardo.
When you're about to, but you're not.
Energy that is stored. Good. So when you're about to, so you have your energy stored, and then it turns into kinetic. Vivian, give me a definition for kinetic energy.
Energy in motion.
Energy in motion. So we start with potential and end with kinetic. What, or not end with kinetic, we turn it into kinetic. Usually end with potential. What do we all have right now? What energy do you all have?
Potential.
Potential energy to move. Yes, sir.
Like if you have a pencil and you throw it.
And you drop your pencil. Right now you're in potential, but once you drop it, there's the kinetic. It's in potential again because it's not moving anymore, right? Okay, who can give me a definition for light energy? We talked about it yesterday when you guys made your posters. Miguel.
The sun.
The sun? Can you give me that? That's an example. Can somebody give me a definition or like their own rendition of a definition? Give me.
Light energy.
Light energy?
I think the definition of light energy is when like energy that is that can make light.
That can make light. So energy that you can see, right? Because every time you have light, are you able to see? Mm-hmm. So when you're driving at night or when you're in a dark room and then the light comes on, you're able to see, right?
Yeah.
So light energy is energy that you can see. Okay? So today we're talking about thermal heat energy. Who can give me a definition for thermal heat energy? Anybody have a rough guess? You can look in your notebooks. If you finish your charts, you can look at the chart on the back of the room. That's how to resources. Andrew?
Energy that can change in temperature.
Energy that causes a change in temperature. I want you to write this in your notebook. So when you turn to this page, you know exactly what thermal heat energy is. On this page? Okay, do it on this page. Energy that causes a change in temperature. On the right side. Okay, Miguel, tomorrow or on a day we do something, make sure you really do 2 pages. Cause I can't use this page. So we're gonna do your own observations, right? We have our in and out page. Make sure you have an in and out page. Okay, who can give me an example of thermal heat energy? Fire. How would you be able to tell that it had heat energy, Alex? Like if somebody had never been next to a fire before and said, oh, fires get hot, how would they know? If you get close to it, you change temperature, right? So energy that causes a change in temperature, when you're away from a fire, maybe you're camping and it's cold outside and you're kind of chilly. And then you get next to the fire and it causes a change in temperature and you get warmer. So you're receiving that heat energy from the fire. Can somebody give me another example? Lauren.
The sun.
The sun. So same thing with the sun, right? When you're out at the beach or you're out playing, you get really warm and the sun feels like it's beating down on you. You're receiving that heat from the sun. What else receives heat from the sun as its fuel? The plants. Do you know what that transfer is called? Photosynthesis.
Oh.
It's receiving the heat energy from the sun and it uses it as its fuel.
A flower.
Like photosynthesis. Wow. It receives the heat from it. Anybody think anything?
Stars.
Stars. They're balls of fire, right? You can put a star off of fire. What is the example that I use a lot when I'm talking about heat and I tell you guys to feel something warming up? Here. Rubbing our hands together. Does anybody know what that's called? When you get heat from rubbing 2 things together.
Fire.
It's called friction. Friction.
Why do people call it friction?
Because that's the definition of when 2 things are opposing forces. So one hand's going this way and one hand's going this way. And they're creating that force and they rub together. So then you're transferring heat.
Okay.
So friction, rubbing hands. What else can you rub together to make heat?
Rocks.
Rocks and sticks. So y'all have seen in pictures or movies when they're trying to make a fire and they rub the sticks together or they try to make the spark from the rocks. Somebody said spark. Rubbing hands and rocks and sticks. I think you guys got a good understanding of that. You guys did good. So when you're rubbing sticks together or rocks together, what other kind of energy are you using? Marta, do you know?
I'm using something they use in fireworks.
No, that's chemical.
A chemical reaction.
There's no chemical. When you rub 2 rocks together, is there a chemical reaction? No. Eric?
Mechanical.
A mechanical. There's also mechanical. So mechanical energy can be used to create heat, right? Because you're putting that force, if you're using the rocks, you're using your own hands to create that force. And then by hitting them together. Like when we did the pendulums, and they hit together. When they hit together, there was a little bit of energy because they collided. Right? So today, I'm going to talk about transfer of heat. Is somebody at the door? So I'm talking about transfer of heat. So when 2 things are different temperatures and you put them together, so I'm going to give you an example. If I put an ice cube, a cold ice cube, into a Coke that I just pulled off of the side of a table, what's going to happen?
No, it's
will melt, what's going to happen to the soda?
It's gonna
It's going to bubble.
get.
What about the temperature? What's going to happen to the temperature? It's going to get cold. When you put ice into something that's kind of like warm temperature or room temperature, and you're like, oh, this is gross, it's warm. And you put ice into it, it matches the temperature, right? So the Coke or the soda is taking the heat or the temperature from the ice, and then the ice is also taking the heat or temperature from the soda. So one is getting colder while one is getting warmer, and that's why the ice starts to melt and shrink. So that's a transfer of heat thermal energy, right? Yes, Jim.
And whenever it's in placing it,
Because the hot air hits the outside. So my water bottle's over there, and it's probably has condensation on the outside. I got ice in the inside, and what's hitting it on the outside?
air.
The air, and it's warmer than what's inside the bottle, right? Okay. So today we're going to be testing. I'm going to give everybody a paper clip. I don't want you to do anything with the paper. I'm just going to set it on your desk. I don't want you to touch it. I'm just setting it on your desk. You can look at it. It looks real pretty. I know some of you have never seen a paper clip before.
They're so pretty.
They're so shiny and nice. You can just observe. Oh, nice and shiny. Nice and shiny.
So shiny.
Okay, I want everybody to pick up their paper clip and just hold it. Everybody do this.
Shiny.
Just hold
So
it.
cold.
Okay. I want you to take, or on the outside, where it kind of, you can fold it out. I want everybody to fold it out. So it kind of makes like an L shape. Can I help you? You need to hit the gym, man. You need to hit the gym.
Well, because you're responsible, you're not going to do anything extra, right?
Everybody got it?
Yes,
Once you got it, let me see. Good. Once you have it, hold it up so I can see. You got it, Jackie? So you want me to help you?
It's Alexis. It's Alexis card.
Good. Good. Perfect. Okay. So what we're doing next, hey, eyes up here. We're going to be moving this part of the paper clip back and forth. So I'm going to show you guys first, and then you guys can do it. So you're just going to start to bending. It might break, but it shouldn't if we only do it a few times. So you're just going to go back and forth and try to keep bending it. And I want you to do it probably about 6 or 7 times. Just keep bending it, and then after you're done bending it, either touch it to your hand, or you can touch it to your lip, because your lip has sensitive skin, so it can feel heat. Over. Okay, so I want everybody to start bending it 6 or 7 times. Okay, bend it. And we need to unbend it some more and do it in another place, but it has to be in the same place on the paper clip. Jason and Lauren, paying attention? It has to be the same place. Do you feel it? Oh, I feel it. Ow. It shouldn't hurt. It's warm, right? You do it? Oh, it's really warm. You do it? Okay, so you bend it. It has to be in the same place so that the friction is in the same place. And you finish it up. You get it? You just bend it back and forth. Huh? It has to be in the same. It doesn't matter what part. It just has to be in the same part. Is it warm? You feel it, Jackie? You want me to do it and then you can touch it? It's a little warm, right? There, you guys feel it? You did it wrong? There's no really way you can do it wrong.
I'm strong. I broke mine. You broke yours?
Okay, set your paper clips back down. That's ready for two.
I broke mine.
Feel it? What is that? Because it's metal? Yep, when you're wearing a seatbelt and it gets really hot. Okay, did everybody feel it? Did everybody get a chance to feel it? Everybody's worked? That's okay. That means you're really strong. That means the friction is so strong. Okay, eyes and ears. Who thinks they know what happened when we did this? Why was it warm? Talk to your table groups. Why do you think it was warm?
Because it's desired.
Everybody give your idea.
I don't think we're going to because we were doing some work.
How do you spell it?
That's what you put.
The and part.
She wasn't finished talking.
What do you guys think? Why do you think it got warm?
Because you were beating it too fast.
You're biting it fast?
What?
Right? And it was in the same spot, right? Oh, with our fingers, you think? Some of the heat from our fingers got on it? Because our hands are warm. Oh. What do you guys think? Maybe your hand has throwing heat onto it?
Is it because you put the freaking J? And then she hands me the picture. Okay, so what is it?
Because she put this right on.
It's getting
What do you think? It got weaker and it got warmer.
They never come dangerous.
Okay. So, Jimmy's table. Somebody give me Jimmy. Why do you think the paperclip got hot?
Well, I think it's like friction, and I also think it's because of the heat of our hands that we're bending it. It's like that.
It's like that?
It's like tape.
The heat is transferring from our hands onto the paperclip?
Yeah.
Lauren, what did you say?
I said when I think it got warm because when we were bending it, was like heat, from our hands getting to the paperclip because we kept on moving them.
So the heat from our hands was so close to that part that it transferred to it?
Yeah.
You know what I'm saying? Okay. Do you guys have a different one?
I think it was in there because we might put the paperclip in
Like warmer? Yeah. So the transfer of heat from our palms, do you have them, Charleston? No? You don't have a guess as to why?
I think we were going too fast.
You're going too fast? So the faster you rub your hands together, the warmer it gets, right?
It's black inside.
So part of it is friction, right? Inside of a paper clip, the way that it is made, there are little iron strings on the inside. So when you're rubbing them together, the iron in the middle, when something gets warm, everything is moving faster, right? So the faster you were moving it, right, the faster you were moving it, the faster what was inside the paper clip was moving, and it was getting warmer and warmer.
And then until the part where it broke.
Into the part where it broke. He went so fast that he tired out the wires and they broke.
Me too.
Okay. Can I have Anna, can you go around with your journal and hold it in like a V shape? And everybody's gonna put their paper clips into her journal and she'll throw them away for us because they're all a little mangled now. No, you may put it in. Nobody may keep their paper clips. Everybody has to turn it in. Anna, he's gonna tell me if somebody doesn't turn theirs in.
Oh, come on.
I can't really see 'cause they're so small, but like tiny little iron parts. So when we were moving them, those threads were getting warmer and they were rubbing together and they were creating friction inside the paper clip. Okay, coming around. Charleston. Jimmy, what you up for?
Here, you forgot this.
Thank you, Anna. You need that right now. Oh, you dropped it, Anna. Okay, last table. money for collecting them. Go ahead and do it. Miguel, what you doing? Give her your paper clip. There you go. You're taking up time. I want to get to the next part. Thank you, sir. Who can tell me what this is?
Thermometer.
A thermometer. It comes in different forms. This is one of the forms of a thermometer. I'll show you some other ones too, just to look at them.
Is it like one of those thermometers that like that it shows you when they're sick? Yeah. When you're sick.
No, that is a thermometer, but you wouldn't put this in someone's mouth.
Is it for food? It's a sanitary one.
For a pool, it can be in a pool. A thermometer for when you're sick. Have you seen the new ones that they don't put in your mouth?
Yes.
And they rub it
Oh,
either on
yeah.
your forehead
Oh,
or you
yeah.
stick it in your ear?
Yeah.
So the heat energy from your forehead when you have a fever, or it comes through your ear too because it's inside your head, it transfers onto that thermometer so it can tell the doctors if your head is a little too hot. So it takes that heat energy from your body. Okay, so here's one thermometer. Where would you find this thermometer? What do you think? In homes, grocery stores, pools, people's walls. It's on walls a lot outside, right? So if you go to like a public pool, or maybe you have one at your own pool and it's sitting on the wall, and it usually tells the outside temperature.
I got one for rain.
For rain.
To measure rain?
To measure rain?
Yeah, there's one to measure rain.
Not on that one. It doesn't measure rain. That just tells you the temperature. And then there's this one right here. There are little beads in the bottom.
Awesome.
From what we know from heat and moving things, what do you think would happen to the beads the hotter this got? They wouldn't pop, but they would move. They'd react to the heat, right?
Would they break out?
No. I think they would just kind of vibrate together, and that would tell the thermometer how hot it's getting.
Oh, cool.
And this is the one we're going to be using today. What are the two? Yes. Which one? This one? This one? What does anybody know what the stuff in the bottom? I'll walk around it. Does anybody know what the stuff in the bottom is? The red?
Liquid. Yes.
Liquid red. What's the name of it? Does anybody know the name of it? Not blood. Not a glow stick.
It's a red line.
It's called mercury. Mercury reacts with heat. So when it's reacting, like you said, Eduardo, when you guys said the little balls in the bottom of this one would vibrate, mercury reacts to heat by expanding. So when it gets warmer, it reacts and it starts to go up on the thermometer. So we're going to be using this one today. Yes. Touch what? The mercury? I don't know. I never tried and I don't think we should. Okay. So in your science journals, on the left side.
Predict what's going to happen if you put something on something? Yeah.
No. Not yet.
Yeah.
I want you to put a grid.
Oh.
It's going to be cut into fourths.
That's alright.
Oh, no, actually it's going to be cut in, yeah.
Is it on the left side or the left?
The left side. Because you're recording your observations. I'm not going to give you the answer.
Can it be like really big or does it have to be like small?
If you want to make it half the page, because you don't need...
All of it.
It can be half the page.
I didn't read it.
That's as big as I want. That's the biggest it can be. But don't make it too small either, because you have to write in the grids. For real.
I'm gonna see. So.
Okay.
It's not asking right here.
Okay, all you need to do is write the grid and then fill in these squares.
You have to write that in a little box. Can we take up all the
This one, yes. Okay, Jason and I don't inside conversations right in the box. Yes.
Is it like we're gonna write here and then it's gonna
And then we're gonna write something on the other side, right? So on the left side of your grid, on the top one, you'll put temperature before mixing. and temperature after mixing.
Yay.
So who can predict what we're going to be doing?
Also mixing.
Mixing something.
Yay.
Yep, it's right in there. Right in those two. Okay, don't take too much time. You gotta get it down too. Good, Jimmy. Go on. You want to try temperature before mixing and temperature after mixing. And I'll tell you what to put in the other ones. There are going to be blank spots that you'll fill in. And I'll tell you what to put in the blanks.
What would I put?
Okay, somebody, when you are telling someone the degree or the temperature of something, how do you say it?
It's
56.
94 degrees
94 Fahrenheit. Has everybody heard the word Fahrenheit before?
Or Celsius.
Or Celsius. Good. So Fahrenheit and Celsius. Today we're just going to be reading Fahrenheit. So on the right side of your squares, and write a little line. You're gonna write Fahrenheit. F for Fahrenheit. That's the only thing you're going to be putting in that square. So it can be pretty large. F for Fahrenheit. I just put the line because that's where you're going to be writing the temperature. We're not mixing a temperature, but we're telling the temperature. Okay, I'm going to fill this with water. Right, so I put ice in this water before class started, but the ice has melted.
But did it have
No, I'm going to put the thermometer. In here, and it will give me the temperature. I'm going to have each table come up, and you're going to line up, and you're not going to say what the temperature is, but I want you to read the thermometer and remember what the temperature is and write it in your chart. So have we mixed the water yet? No. So this will be in the temperature before mixing boxes. Everybody understand? Temperature before mixing. Say it with me. Temperature before mixing. Good. So I shouldn't see any in the bottom box for after mixing because we have not mixed it yet. I'm going to put this thermometer in here. And then I'll have, once it kind of adjusts to the temperature, I'll have you guys come up and look at it. And when you see the temperature, do not say it out loud because everybody's going to have a chance to look at it, and I want to make sure everybody can read it. Okay? Do table 1. Come on up. Look inside, look at the thermometer. You're reading Fahrenheit on the right side. So look at it, keep the temperature in your head, and go write it in your journal. Don't say it out loud so everybody can see it. Once you see it, go back to your seat because everybody's got to have a chance to do it. Okay, just right. Is it the what? Oh, the Fahrenheit? It's on the right side. There's an F in the bottom, which is in the water, so you can't see it. Okay, once you see it, hop back to your seat and write down so you don't forget what you saw. Fahrenheit is on the right side. The F is in the bottom in the water. The green thing? Oh, the green has nothing to do with it. That's just telling you a specific number. You're looking at the red to where the red stops. To where the red on the thermometer Don't say it out loud. Just go right in your notebook. You see it? If you see it, go back to your desk. Everybody else has to get a look. It's on the right side. The number's on the side. You can, and then you'll know how to round. Numbers come between 60 and 80. What 10 comes between 60 and 80? Sure. Go right down. Okay, Jason's table. Karina, I'll bring it to you.
So I put it where before? Yes.
We only said it out loud together. There you go. Good job. You see? See it? See it? Want to see it? Head back to your seat. Okay? Okay, Jimmy's table coming up. Right now, I'll bring it to you in a second. Thank you.
It's just on the ice.
As a result of this lesson, the students learned the differences between kinetic and potential energy. By creating the pendulum and conducting observations in their notebooks of the pendulum's movements, the students learned what it means for an object to have potential or kinetic energy. What I liked most about this lesson is that the students were able to make hypotheses using their pre-existing knowledge and then work with their classmates to design the pendulums and test their hypotheses. The students were able to observe the forms of energy in motion and record their observations in their notebooks. The students practiced using the scientific process, beginning with the question, when does an object have potential and kinetic energy, and concluding with what they observed using the pendulum that they built. In this lesson, I learned that inquiry is key when teaching any science lesson. As a teacher, playing facilitator during science lessons is beneficial to the students because they can make their own inquiries about questions rather than having the teacher provide the answers for them. Allowing the students to make discoveries on their own and with their classmates is a successful strategy for promoting well-rounded other understandings. When students work together to discover the answers to a question, just walking around as a teacher, you will hear many different answers. Walking around, you will hear students giving examples that they may have witnessed in another class or anything using their prior knowledge, and the students use their classmates' contributions to help shape their own answers. All students think differently, and when they work together, they combine their ideas to form well-rounded discoveries. If I were to reteach this lesson, I would change the way that I modeled creating the pendulum. A lot of the students were confused on how to build the pendulum with the materials they had. They had a ruler, a string, and weight washers. A lot of the students were confused on how to build them, and if I had provided more structured and clear step-by-step instructions, the students would have constructed their pendulums in a more timely manner and would have had less questions. I also would have spent less time roaming around the classroom trying to help each table put together their own pendulums. So if I had formed more clear instructions, the students would have been able to follow along more accurately as a class. Another thing I would add to my lesson would be more real-world applications. During the lesson and in previous days, we had talked about roller coasters and at what point a roller coaster car has potential or kinetic energy. We also talked about when someone is on a playground swing, at what point when they are swinging do they have potential or kinetic energy. If I were to teach the lesson again, I would create a slideshow using pictures of objects that have potential or kinetic energy and ask the students to tell me which form of energy the picture is showing and explain how they knew that it was either showing potential or kinetic energy. I would add this at the end of the pendulum observations to assess the students' understanding of potential and kinetic energy. Overall, I think this lesson went well. The students participated well, worked well in teams, and were engaged in their learning. At the end of the lesson, the students drew pendulums in their journals and labeled their drawings, which was one of our goals. And looking at their journals at the end of the lesson, I assessed that students demonstrated understanding of the information that had been taught by looking for where they modeled their pendulums, when they modeled that they had potential or kinetic energy, and also by providing small samples of explanations on how they knew which was which. So I hope you enjoyed the lesson. Thank you.